Hello. In this video, we're going to take a look at putting together the algebra and the calculus to sketch the graph of a rational function. And so we've got a real simple rational function here, x plus 6 over x minus 6. So first of all, the domain of this function, remember we cannot have 0 in the denominator of a fraction, so that means x cannot be equal to 6. So our domain is going to be negative infinity to 6, and 6 to infinity. We want to find the x-intercepts here. X-intercepts are going to be whenever we set y equal to 0 and solve for x. And we're going to multiply both sides by that denominator. 0 times that denominator is still 0. The right-hand side times that denominator, the denominator is going to cancel out, and we'll be left with that numerator, x plus 6. And so we have an x-intercept at negative 6, 0. Y-intercept is going to be whenever we plug in 0 for x. So we'll get 0 plus 6 over 0 minus 6. That's going to simplify to just 6 over negative 6, or negative 1. So our y-intercept is going to be the point 0, negative 1. And if we want to find the vertical asymptotes, remember vertical asymptotes are going to be when you reduce the fraction as much as you can, which ours is already reduced, and set the denominator equal to 0. And so we do have a vertical asymptote here at that one place where our domain breaks up at x equals 0. We have a vertical asymptote. And horizontal asymptote, remember that is the limit as x approaches either positive or negative infinity of our function. And so if we take that limit, we're going to actually get the same thing whether we plug in positive or negative infinity here. So I'll just stick with positive infinity. In college algebra, I teach Bobo Botten. Bigger on bottom, 0. Bigger on top, none. And then if it is the same, we're going to look at the leading coefficient over the leading coefficient. This we do have the same because what we're looking at here are the degrees, the biggest power on x, and those are the same. So this is going to be, we are going to get the leading coefficient, which is an understood 1 on both of those x's. So that limit is equal to 1. That means our horizontal asymptote is going to be y equals 1. You can also divide each of these four terms, the x, the 6, the x, and the negative 6 by x, and approach it a little more analytically. All right, so that's all for the algebra portion of it. Now we need to find where this function is increasing or decreasing. So in order to do that, we need to take our derivative. So our function x plus 6 over x minus 6, when we take the derivative, we're going to use the quotient rule. The bottom times the derivative of the top minus the top times the derivative of the bottom. Derivative on both the top and bottom there is equal to 1. All over the bottom squared. So if we distribute that negative, multiplying by 1 isn't doing anything. We're going to get x minus 6 minus x minus 6, and that's going to simplify to just negative 12 in the numerator. And then we still have x minus 6, quantity squared, in the denominator. That is our first derivative, and so we want to determine where this is undefined. It is undefined if x is equal to 6. That's already a point that we've noted as far as our domain. It's our original function is not defined there as well because we have a vertical asymptote. And if we try to set this equal to 0, multiply both sides by that denominator, and we're going to get 0 equals negative 12. That is never true. So that means that there are no critical values. That means there will be no max or mins, but we do still have to see whether this is increasing or decreasing, and that can happen at x equals 6. It can change. And so pick something on either side of 6. I'm going to go ahead and pick 0 and 7. We are plugging into our first derivative here. So our first derivative, if we plug in 0, we're going to get a negative 12 in the numerator. If we plug in 0, that's going to give us a negative 6 squared, or a positive 36 in the denominator. So a negative divided by a positive is going to be a negative. So that means our function will be decreasing on the interval from 0 to 6. And then if we plug in 7, we're going to actually have the same thing happen. We're going to get a negative 12 in the numerator. 7 minus 6 is going to give us 1 squared, and the denominator is 1. And that is also going to give us a negative number. So that means our function is decreasing everywhere it's defined. So it's going to be decreasing from negative infinity to 6. And it's also decreasing from 6 to infinity. But because we had no critical values that were in the domain of our function, that means there's going to be no max or min values here. Now we want to find our second derivative to look at the concavity. So if we take our second derivative, you can either use the quotient rule again, but that numerator is a constant. So I'm actually going to rewrite my first derivative as negative 12 times x minus 6 to the negative 2 and use the chain rule instead of the quotient rule. So if we take this derivative, we're going to have negative 12 times that derivative of x minus 6 to the negative 2, which is going to be negative 2 times x minus 6 to the negative 3, and then multiply by the derivative of the inside, which is 1. So if we clean this up, negative 12 times negative 2 is going to be a positive 24. And then we get x minus 6 cubed in the denominator, which is the same thing you would get if you use the quotient rule and then simplified it as much as you could. Again, this is undefined at x equals 6. And we'll see the same thing happen if we set it equal to 0 and multiply both sides by that denominator. We will get a statement that is not true. 0 is not equal to 24. And so that means we will not have any points of inflection. But again, we need to figure out whether this is concave up or concave down. And so now we're going to be plugging into our second derivative, our points 0 and 7. And so our second derivative at 0, now we're going to have a negative 6 cubed. A negative cubed is going to give us a negative number, so a positive divided by a negative. Positive divided by a negative is a negative, so our second derivative is going to be negative, meaning that our function is concave down. And then at 7, if we plug in a 7 there, we're going to get our numerators a positive 24. In the denominator, 7 minus 6 is 1. And that, when you cube it, is going to give a positive number. So a positive divided by a positive is positive. And so our function is going to be concave up. And now we're ready to put all of that together. The only point that we have anywhere in here that really anything's going on, we do have an x-intercept at negative 6. But really the only thing that we have as far as our increasing and decreasing is concerned is 6. 6 is the only place where any of that is changing. And so for our table, we're only interested in x equals 6. And our function was decreasing on both sides of 6. It was concave down on the left and concave up on the right. Just looking at those tables that we put together, I'm just combining those two. So that means if it is concave down and decreasing, it's going to look like the right side of a frown. And if it is decreasing and concave up, that means it's going to look like the left side of a smile. And then if we put that in our graph, we do need to graph negative 6 because we have an x-intercept at negative 6 and we have a y-intercept at negative 1. I'm just putting together everything that we found here. We have a point at negative 6, we have a point at, or negative 6, 0, we have a point at 0, negative 1, We have a vertical asymptote at 6 and a horizontal asymptote at y equal 1. So let's go ahead and graph all of that. So that vertical asymptote is going to be at 6, 3, 4, 5, 6. So I'm going to graph that with a dashed line going down. We have a horizontal asymptote at y equal 1. So I'm going to graph that with a dashed line. And then now we're ready to use our table to connect all those points. So to the left of 6, it's going to look like the right side of a frown, and it's got to go through these 2 points and then get closer and closer to our 2 asymptotes. So it's going to be leveling off just underneath that asymptote. It's going to go through those 2 points and then approach that vertical asymptote. Now on the right hand side, all we really know about the graph is it's going to look like the left side of a smile. But we also know that it does not have any x-intercepts because we did not find any x-intercepts, and we know that it's got to get closer and closer to those 2 asymptotes. So the only way it can have that shape that looks like the left side of a smile and get closer and closer to those 2 asymptotes is if it is in the top right hand corner of our graph. And there you have the graph of x plus 6 over x minus 6. All right, I'll see you guys next time.